So, quick recap. So weak acids and bases fail to associate. We give them a Ka or Kb value. All Ka and Kbs are less than 1 because these don't fully dissociate. The bigger the value of K, the stronger the acid or bases in the realm of the weak things. All right, and then again, weak acid or bases make better conjugates than water, which is why they're in equilibrium. Okay. No, because they can't. So, let's just say, you got like 0.1 is what you're starting with. Well, if it doesn't fully dissociate, it's got to be less than 0.1. So pick any number less than 0.1. Sure. Now, technically, if these are both 0.01s, this would become 0.09. Remember, it's a 1-to-1 ratio. So if like only this much comes out, then it only lost that much. Right? If this was HX, let's say this is HF. This is H plus, this is F minus. So initially, these would start off as 0. So then, right, so it's the ice problem. So if you're telling me at equilibrium they're 0.01, which is again, then these would be, the drop is 0.01, so this is 0.99. Nope, 0.09. If we did the math, 0.01 squared divided by 0.09, that's definitely going to be less than 1. It always works out like that. Because since it doesn't fully dissociate, your denominator has to be bigger than your numerator. But if this was, you're saying this was 0.01 and this was, can't be. How could this be 0.01, this be 0.09? This means this more of a dissociated. It can't be bigger than this amount ever because this is as much as you've got. So it's either the same or it has to be less than that. That's because like whatever the concentration of your acid is, the most your ions could be is the same. They can't be more because there's not more for it. Like where's it coming from then? So no matter what, it's either the same strong acid or it's going to be less, which makes K less than 1. And that's mathematical, that's why it's like that. Of course, yeah, no problem. All right. All right, occasionally we get the pKa. Guys, P is the same thing as it just means negative log. So the negative log of Ka is the pKa. If you want to go backwards, Ka is 10 to the negative pK. It's the same thing we did with pH, same idea. Okay. Again, this is really, everything is opposite. Everything is like opposite day in Unit 8. Ka and pK are inversely related. So the bigger your value for Ka is, the smaller your value for pKa is. Vice versa. You have a really small Ka, you have a really big pKa. That's really weird. I don't like it. So, in my humble opinion, if you ever have to compare things, just get everything to K. To me, K makes sense. It's not opposite. If K is big, you're strong. If K is small, you're weak. I like that much easier. It's not inverted. So when we do titration curves, pK is called like half equivalence point is the pK. So when you build a buffer, you want to choose acids and bases who have a pKa really close to your target pH point. So for example, in a lot of food, you'll see citric acid and sodium citrate, because that's a common buffer. It has a pKa of around 4, and a pH of 4 is very antibacterial. So food that's shelf stable will have that in there because it keeps bacteria out from growing there. So you choose a pKa that makes sense for you. And again, this makes it easier to look at on a scale, but as far as comparing, it's easier, I think, to compare numbers when they're just biggest and smallest. The P flips everything because it's the negative log, so all the scales get inverted. But this has like real value. It's not just for fun. Like, it's not just to piss people off and make up a random number. Like, there's legit value to it. Your blood has like a pH of like 7.5. So if they needed to make a blood buffer for you to give you like a blood transfusion, they would choose a buffer that has a pKa close to the same pH as you. So like that's what it would be easier. And it's easier to find this value on a chart than looking up a bunch of numbers with scientific notation. So in this problem, there are 4 technically forms of acids here. It says, which of the following is the strongest acid? So strongest acid, right, means biggest Ka. Well, between the second and the third one, they're already both in Kas. Which one isn't the answer going to be? Which one is the smaller of the two? Yeah, so we know it's not this. Now, I can't compare 3.74 to this number because this is pK and this is Ka. So I'm going to turn both of these into scientific notation by just doing 10 to the negative of this and then 10 to the negative of that. So this is going to be 10 to the negative 3.74, and this is going to be 10 to the negative 7.21. Could you guys figure out what the bottom one is? And I will do the top one. I'll do 10 to the negative 3.74. What'd you guys get for this one? Okay. So now, if we look at the other 3, H2CO2H, H2SO3, and CO3 minus 2, of those 3, who has the biggest Ka value? So this is, of these 4 acids, this is the strongest acid. Of the 4, which one's the weakest acid? Yeah, there you go. In fact, real quick with the bottom one, guys, what do acids do? They donate does this thing have any protons left to donate? It's -2. It doesn't want to give, it wants them. This actually isn't an acid, this is it's a base. Oop, that's the wrong laptop. All right, let's try another one. Each solution below is at 25 degrees Celsius. They all have the same concentration, 0.1 molar. Place them in order from lowest to highest pH. aka place them from the most acidic to the most basic. Now, there are 1, 2, 3, 5 of them. Do you guys have 5 or do you have more than 5? Okay, you have 5 too, right? Okay. let's label these. So this is going to be, there are 5. So lowest will be 1, and then the highest pH is going to be 5. Real quick, scan the 5 acids. Are there any strong acids on the list? Who's the strong acid? Yeah, so because it's a strong acid, it's going to fully dissociate. It's got the highest concentration of H+, therefore it has the lowest pH. So number 1 is going to be HBr. Let's look at the extreme opposite end. Are there any strong bases on the list? So that's going to have the smallest amount of H+ ions. Therefore, it's not going to have the lowest pH, but the highest. So this is going to be 5. Now, if you look at hydrocyanuric ammonium and chooch, I'm not going to say their full names, and I won't give it away. Look at these values. One of them is different than the other ones. Who's different? HCN, NH3, or chooch? What's different about NH3? So that's telling you NH3 isn't an acid, it's a... So if the highest pH was our strong base, our next highest pH isn't going to be our strong base, but our weak base. So this is going to be number 4. Well, now, by the way, between hydrocyanidic acid and acetic acid, who's the stronger acid? Who's got the lower pH? We can tell by looking right here. So they're, right, it's like, you know, who's the tallest short person, right? Like, which of the two is the biggest number, even though they're all less than 1? Is it HCN or chooch? So we're going to learn that in a second. Hold your question. It sounds really rude. Hold it. Let me go on like 1 or 2 more slides to show you how we do calculations, and then I'll come back and maybe you'll see. Maybe it'll make a little more sense then, rather than trying to answer without you seeing like the next part. That's all. But no, it's a very valid question. But when you see how we do the calculations, then maybe it'll make sense why your question like technically doesn't really apply. But makes perfect sense knowing your realm right now. It's a very valid question. But just hang tight for a second. Anything else I can do so far? Chelsea, good so far? I know it's a lot. All right. Let's calculate. Oh, we gotta do this. Percent ionization. You very rarely are gonna get asked this. But to find how much you ionized, it's the amount of H+ or OH- ion over the initial content times 100. To turn into a percent. That's all. We don't, again, need to do this, but we like crush this. Like we beat this thing to a pulp last unit. If you dilute an acid, it will always ionize more. And it goes to Le Chatelier. Q ends up being less than K, so the reaction has to go to the right, and it further ionizes. That's always true. Always true. So if you have a 0.1 molar solution and a 0.01 molar solution, and they're both of hydrofluoric acid, if you asked which one has a greater percent ionization, it's this one, right? Because it's got a lower concentration. All right. Let's put it all together. What time we got? All right. I think once you see one of these, then we can start helping you out with that question from before. So these are the big daddies of weak acids and weak bases. And this is all we're working on today after the 2 problems in the notes. This is homework, like this is all we're doing. If we can master this, we're gonna be able to do fine as we move on. All right, so we have a solution of boric acid, it's H3BO3, has a pKa value of 9.23. Write the equation for the reaction of boric acid and water. What's the Ka value for boric acid? Find the pH, and then what is the percent ionization? All right, that's a lot of questions. So let's start with question 1. All right, H3BO3. Let's try this again now. H3BO3. Because they're telling you to add water, we should add water. Is H3BO3 a strong acid? No. So this is not a one-way arrow. This must be in equilibrium. And guys, acids will only donate 1 proton at a time. So even though there are 3 H's, it's only going to donate 1 of them. So if this loses an H, it's H2BO3. And if you lose something that's positive and you were originally neutral, what's your new charge have to be? -1. This was the acid, water is the base, so this proton from the boric acid became H3O plus. What was the pKa? I can't. 9.23. Okay, so try to find the Ka, and then we'll come back after the bell rings again.